We're going to also talk about the standard error, and that formula is right here for that. And oftentimes in the table, that's going to be given to you as well. And I'll point that out as we do our example. When you're doing these conditions, the T star is the critical value, and our degrees of freedom are a little bit different this time. Our degrees of freedom are n minus 2. And our book will tell us that the n minus 2 is beyond the scope of what we're doing here. There's a long explanation of why it's n minus 2 and not n minus 1. We're not going to worry about it. And it's talking about negative t to t. They're talking about, oh, we have a confidence interval. We're going to go on either side. That's where the plus or minus is coming from. So, although we have the standard error b, it says here, you're not going to have to calculate it by hand. We're going to have some kind of output. And we're talking about, when we look at the statistic, we're curious about what's happening with the slope. That's the main focus of this section, the slope of this regression line. And so when we do our confidence intervals, as we're going to see on the next slide, we're going to state what we want to estimate. So we're going to say, just like we have in the past, we want to find a 95% confidence interval for the true slope beta of the true regression line. And then relating, and then you talk about whatever is going on in the context of the problem, just like we have in the past. When you're planning, we have to do the different conditions. Those are the liner things. And we're going to use a t interval for the slope to estimate b. So that's kind of new. This time, this is what we're going to say for our test, or our confidence interval. A t interval in this case, because we're doing confidence intervals, for the slope to estimate beta. Then we do this stuff. So we use our two formulas. We talked about those before, just up above. Here are the two formulas that you're going to need. That's what's new in this section. And then our conclusion is the same as always. We are 95% confident that the interval from blank to blank contains the true slope blank of the regression line blank.
Or one.
Yeah, that's the when we do the test, not the confidence interval. And we'll do that tomorrow. So let's try one. So here's a table. And earlier we were talking about Minitab with those 4 pictures. And so here's another part of the Minitab stuff where they actually give you some data. And they do a least squared regression analysis. That's what you see up here on the board on these helicopter drops. And remember, it came from 70 helicopters, so that's kind of important. Don't forget about that. There were 70 of them. So that's our n, which means our degrees of freedom is n minus 2, which would be 68. Your table doesn't have 68, so you have to go to the more restrictive one, which would be 60 in the future, just for your information. And what we're going to do is we're going to find the standard error of this stuff and talk about it in the context of the problem. So as you look for the standard error, what you're going to see is they tell you the SE coefficient. And they're talking about the standard error of the slope. So the slope is not your constant. The constant, this is your... Oh, this stuff, the constant is the... So we have y hat equals a plus bx. This would be the a thing. And then your drop height changes, that's your b stuff. Or in other words, your slope. So when they talk about the standard error of the slope, what you're looking for is something that has to do with b. And then you look for the standard error, and oh, look, here it is. Standard error of the slope. So I just write that down, and you call it standard error of my slope b, and that's 0.000218. And then if you want to know what it's saying, it's basically saying if we repeat this experiment many times, the slope of the regression line would typically vary by 0.000, I'm just going to go to 2. You know it's 0.18 afterwards. From the slope of the true regression line when predicting drop times of the helicopters. So our true slope out there somewhere, like if we took every single helicopter and every single drop, has a slope. But when we take a sample, Sam takes a sample, he gets 0.3. And Aaron takes a sample, he gets 0.32, bless you. And John takes a sample and he gets 0.27. And on average, if we do this with multiple samples, what we're saying is on average we're off by 2/10,000ths of the true slope. That's what they're saying. In the next part, we're going to do a 95% confidence interval. This is kind of the big deal that we do in our class and have been doing for the last 4 chapters. So here we go with the 95% confidence interval. We make our statement first. And our statement is, we will find a 95% confidence interval for the true slope, which of course I told you a little bit earlier is called beta, of the true regression line relating flight time, which was our y value, and drop height, which was our x value. I guess you could say of paper helicopters. So that's putting it in the context of our problem. The next part is we would say something about what we're going to do. So that's the statement, and then the planning part is we will calculate a t interval for the true slope beta. So I'm going to say that right now, let's see, our 5 conditions have been met, and you could say see above or see previous slide, whatever it was. So for me it's a previous slide, but for you it might be the previous part of the problem on the AP exam, and that's okay, you can do that. And then after this part's where, so I talked about the conditions in the test, now I'm going to talk about the actual doing of the math. So we know that first of all we're going to calculate B plus or minus our T star statistic times SEB, which was the standard error of our slope. I know that my degrees of freedom are going to be 70 helicopters, take away 2, or in other words 68. You will notice that in your table you don't see the 68. Remember, you have to be more restrictive. So I'm actually going to use instead 60 for my degrees of freedom. You find out, so this is what we're going to use from the table. You're going to find out that your T-star statistic is equal to 2.0. So, after we have all this information, we're going to actually show the math afterwards. So here's all the prep for that. And so now we have, from our data table up above, so if I scroll up just a little bit here, I hope I can get, maybe I can't. Okay, so look at your table on the slide, bless you. And I have that the B is 0.000, no, 2 zeros. 5, thank you. 7244 from the table. And that's going to be plus or minus our T star, which is 2.000, whatever it is, times whatever our SEB was, which we talked about earlier, and that was 0.0002018, I think. that we wrote down later. If we write this in our interval, we find out that our interval is actually going to be going from 0.00531128. I don't know that you need to go that far. I probably would go 3 places past the 0, so I would have written down 0.00531. I think that should be sufficient. And then 0.0061270. Again, I probably would have gone 613. Because remember, you have to be accurate to 3 decimal places, but I like to go 3 past the zeros. That's just my preference. And then we draw our conclusion after all this information. So in our conclusion, what we're going to be saying is that we are 95% confident that the interval from 0.00531 to 0.00613, notice how I changed them to the numbers, captures the slope of the true regression line I think you just go with slope. Hang on, Aaron. Relating. Oh, shit. Sorry, got distracted. Capturing. No. That's not what I want to say. Relating. Sorry. Flight times to drop heights of paper helicopters. What does it mean when you're talking about the 95% confident? And so this is kind of, for some people, for many people, it's really kind of confusing because you think that means you're 95% sure that you have something. It's not exactly that. So in the 95% confidence, the way that it should be interpreted is if our experiment was repeated many times, %, of our confidence intervals would contain, I'm going to use Aaron's phrase, the true slope of the true regression line relating, and I ran out of room, the flight times to the drop heights of these paper helicopters.